Cat channel. Please do remember, subscribe, like and share. Thank you. Hi all, this is the sixth video for chapter 7, Chemical Equilibrium. Today we are going to discuss the calculation part 3, buffer solution, which involve Henderson-Hasselbalch equation. So what is Henderson-Hasselbalch equation? Before we start to know the Henderson-Hasselbalch equation, we are going to look at how it derived. First, we have to write down the equation for weak acid. We are using ethanol acid or acetic acid. Okay, write down the K expression, concentration of product over concentration of the reactant, and then we take out the concentration of H+, so we will get the Ka times concentration of ethanol acid over the ethanol ion. And then taking the negative logarithm of both sides, then we will get negative log concentration H+, so this is pH, and the negative log Ka, so this is the pKa. Okay, since positive is this is one of the properties of the natural logarithm, so we will positive log, so reverse for these two concentration, and then we will get the pH equal to pKa plus log, this is the conjugate base, over the weak acid. Now, before we proceed for the calculation, we have to know there are two assumptions when Henderson-Hasselbalch equation is used to determine the pH of the buffer solution. The first one, we need to assume that the concentration of weak acid is equal to the concentration of the acid used, though the degree of dissociation of weak acid is very small. Number two, the concentration of the conjugate base is assumed to be equal to the concentration of the salt, because salt is completely dissociated. The volume of salt is too small and can be negligible or ignored. It does not affect the concentration of the salt. Now let's check for example 1. What is the pH of a solution containing 0.3 molar HCOOH and 0.52 molar potassium methanol? Okay, this is methanoic acid. Ka is given. So let's check. We have to analyze the question. First, the initial concentration of the acid compound is 0.3, and then this is the concentration for the conjugate base or the salt, which is 0.52 molar. So write down the formula and then substitute. Okay, conjugate base is HCOO negative, and then the weak acid is HCOOH. Now we value and then press the calculator, and then we will get pH equal to 4. So be careful, must substitute. Okay, what is the conjugate base, what is the weak acid, and then substitute the value for the pKa and the concentration of the conjugate base and the weak acid, and then press the calculator carefully, and then we get pH equal to 4. Next, this is the Henderson-Hasselbalch equation for weak base. The concept is still the same. We write down the equation for the weak base dissociation, and then product over reactant. H2O is not involved in the Kb expression. And then we will take out the hydroxide ion, and then we taking the negative logarithm of both sides, and then we will get this equation. And then here is one of the natural properties of logarithm, so positive over, this is the conjugate acid over weak base. So at last we get this Henderson-Hasselbalch equation for weak base is POH equal to pKa plus log conjugate acid over weak base. Now check for the calculation. Example 2, pH. Okay, 0.3 molar ammonia, 0.36 molar ammonium chloride, and then Kb is given. So first method, you have to write down the formula, then we substitute, and then we get POH equal to 4.82. But the question asks about pH. So the properties of pH and POH is pH plus POH equal to 14. So pH equal to 9.18. The question asks about pH. So we're using 14 minus POH, we get the answer. Okay, method 2. Okay, analyze the question. So this is the concentration of ammonium 0.36 molar, concentration of weak base ammonia 0.3 molar. So equation substitution. Then, okay, one of the formula is Ka times Kb equal to Kw. Since Kb is given, okay, Kw is a constant, then we can find out the Ka for ammonium. Because the question asks about pH, so we can find the pH through Ka. So pH equal to pKa plus log, okay, weak base over, this is the conjugate acid, okay. So you have to reverse the position of the weak acid and conjugate base as well, and then substitute, you get 9.2. So depends on you, both method acceptable. Example 3, a buffer solution was made by dissolving a mixture of sodium acetate and acetic acid in water. Explain. So this explanation is exactly same as our previous video, the explanation for buffer solution. So first, to write down the reaction happened in the system. The weak acid partially dissociate and the conjugate, the salt, okay, produce the conjugate base, okay, completely dissociate. So buffer system contain this conjugate base and then this weak acid, so that this conjugate base can react with the strong acid when strong acid is added. So this weak acid can react with the strong base when strong base is added. So when small amount of strong acid is added, so it will react with CH3COO negative and then form CH3COOH. So you can, this explanation represent by this equation, one-way arrow. So what happened? Because the production of this reaction is CH3COH, which is a weak acid, so the concentration of the acid remain constant. Only a small change, you can mention that just a small changes for the pH. So the concentration of the conjugate base decrease and the concentration of the ethanol acid or acetic acid increase. What happens when small amount of strong base is added? So the strong base added will react with the weak acid, so form the conjugate base. So the concentration of the weak acid decrease and then the concentration of the conjugate base increase. Since the hydroxide are consumed by react with weak acid, so the concentration of H plus remain constant and then the pH not much changes. Example 4. An amount of 0.984 gram of sodium ethanol was dissolved in 100 ml of 0.1 molar ethanol acid to make an acidic buffer. So over here, right, the question asks about calculate the pH and state all the assumption made. So the first idea we will know, we need to apply the Henderson-Heisenberg equation for the weak base. Okay, pH, pKa, no problem. The value of K is given. Concentration of the conjugate base is not given. The concentration of the weak acid, yes, 0.1 molar. But can we find the concentration of the conjugate base? Yes, by using, because the mass is given. The mass is given, we can divide the mass with molar mass to get the number of mole, and then mole divided the volume. Okay, make sure to change to liter. Solution for example 4. Yes, first find the mole over the volume in order to get the concentration of the conjugate base, which is 0.12 molar. After that, there are two methods. Method 1, we can, okay, take out the concentration of H plus, okay, so Ka times the concentration of weak acid over the concentration of the conjugate base, and then we get 1.5 times 10 to the power of negative 5 molar. So pH equal to negative log concentration, and then we can get 4.82. Or we straight away write down the Henderson-Heisenberg equation and then substitute everything, and then we get the pH equal to 4.82. So it depends on you, both method acceptable. And then what is the assumption? This one we discussed in detail for the previous slide. So we have to assume the acetic acid is weak acid, and then the volume of solid sodium ethanol is negligible. After the simple question, now we move to higher level. Calculation pH of buffer solution before and after the addition of strong acid or base. Let's look at example 5. Okay, the question calculate the change in pH. When 1 cm cube of 1 molar sodium hydroxide is added, so this is strong base added to the buffer solution. So the volume of the buffer solution is 1 dm cube. Be careful, here is 1 cm cube for the added sodium hydroxide, and then the buffer solution is in 1 dm cube, different unit, which contain a mixture of 0.1 molar for the weak acid and 0.1 molar for the conjugate base. So pKa value is given. So first we have to calculate the pH before strong base is added. This is the solution before the pH before addition of sodium hydroxide. Okay, write down the formula, the Henderson-Hasselbalch equation, and then substitute the value, and then we get 4.75. So these are the information we get from the questionnaire. Then after addition of sodium hydroxide. So this is the new thing for you all. So you have to be clear. First of all, the sodium hydroxide is added to buffer solution. Initially, the volume of sodium hydroxide is 1 cm cube. But after it added to the buffer solution, so the whole buffer solution become 1.001 dm cube. And then the number of mole of the sodium hydroxide is changed because initially is 0.01 mole. Okay, why is 0.01 mole? We are applying the mv per thousand. M1 V1 divided by 1000, so the number of mole is 0.001 mole. Now we are going to apply the ice table. Initial mole, okay, for the acid is 0.1 as well. Why? Because the concentration is 0.1 molar, and then the volume of the buffer solution is 1. That's why 0.1 divided by 1 is 0.1 mv per thousand, sorry. M 0.1 times 1, so equal to 0.1 mole. And then the hydroxide we found here 0.01, and then the number of mole of the conjugate base 0.1 as well. So if we compare over here, hydroxide is the limiting reactant with the smallest number of moles. So we minus 0.01 minus 0.01, and then here product plus 0.01. So then we sum up the initial mole with the change mole. So the final mole of the weak acid is 0.099. Now we can find the new concentration for the weak acid divided with the new volume, which is 0.0989. Okay, since we write out the unit over here, then okay, we didn't write over at here. If for safe, better write down the unit as well. So this is the new number of mole of the conjugate base, and then divided by the new volume 0.1009 molar is the new concentration for the conjugate base. To find the new concentration for the conjugate base and weak acid, now we substitute all the value to this Henderson-Hasselbalch equation after sodium hydroxide is added. So this is the pKa plus log the new concentration for the conjugate base. This is the new concentration for the weak acid. So we get 4.76. pH before sodium hydroxide is added is 4.75. After is 4.76. So the changes is 0.01, small increase in pH. So again, proven that the addition of small amount of base to a buffer solution causes only a very small change in pH of the buffer solution. Next, let's move to a more difficult or higher level. Example 6. A solution is made by mixing 500 cm cube of 2 molar butanoic acid. So this is the volume, this is the concentration for the weak acid. With 500 cm cube of 0.5 molar sodium butanoate. So this is the volume, and this is the concentration of the salt or conjugate base. Just now, the volume given is total, but this one separately, given in separately. So Ka is given. Now the question asks, calculate the change in pH when 100 cm³ of 0.5 molar hydrochloric acid is added to 1 dm³. So the total is 1 dm³. 500, 1,000 cm³, so equal to 1 dm³ of the buffer solution. So the pH before addition of hydrochloric acid. First of all, we need to find out the number of mole of the butanoic acid and butanoate ion, because the volume is previously the volume is 500 cm³, but now after the both solution mixed together, the volume is 1 dm³. That's why we need to find out the new concentration of the acid and the conjugate base. Okay, so initially the number of mole is M 2 molar, V 500 divided by 1000 is 1 mole for acid, for the weak acid, butanoic acid. And then this is the number of mole for the conjugate base. Okay, now the volume is 1 dm³. So 1 mole of the acid divided by 1 liter of the acid of the solution, buffer solution, so it's 1 molar. For the conjugate base is 0.25 mole divided by 1 liter, so we get the new concentration for the conjugate base is 0.25 molar. Always remember, write down the unit. So once satisfied out the new concentration for the acid and the new concentration for the conjugate base, now we can substitute the value into the Henderson-Hasselbalch equation. Substitution, so the pH before addition of hydrochloric acid is 4.22. Now, what is pH after addition of HCl? So we need to calculate the mole of HCl added. 0.5 molar and then 100 cm³, so that's why I need to change to liter, so the number of mole is 0.05 mole. Now the new concentration or the final concentration of the buffer solution is 1 dm³ plus 100 cm³, so it's 1.1 dm³. Now we have to write down the equation. For the strong acid added is react with the conjugate base, so it will form the butanoic acid. So this is the initial mole for each of the component. So the added acid is the limiting reactant, that's why minus 0.05 minus 0.05 for the reactant side and positive 0.05 for the product side. So sum up, so the final mole of the ethanol ion is 0.2, and then we divide it by 1.1, so this is the new concentration for the ethanol ion. And then limiting reactant finish consume, okay, because totally react with the ethanol ion. And then the acid is 1.05 mole divided by 1.1 dm³, you get 0.9545 for the new concentration for the weak acid. Again, formula substitution, and then the pH for after addition of hydrochloric acid is 4.1. Before 4.22, after is 4.1. So the changes in pH is 0.12, small decrease in pH when strong acid is added. So proven this is the properties of buffer solution, can resist the change of pH. Now let's proceed with tutorial question 13 discussion. So first, calculate the pH of a solution containing 0.2 molar. Okay, this is the weak acid, and 0.3 molar, this is the salt, means the conjugate base. Ka value is given. So first, when there are weak acid and conjugate base or the salt, meaning that we are going to apply the Henderson-Hasselbalch equation. Okay, B. Explain the change in pH of the solution when a small amount of strong acid is added or a small amount of strong base is added. So this is explanation. Okay, this we discussed already in previous video. So let's check the answer. So first, using a Henderson-Hasselbalch equation, formula substitution, and then we'll get the answer 4.9. Okay, I think should be no problem. Explanation for acidic buffer solution. First, you have to write down the buffer solution at equilibrium is with this equation. And then these are the two reactions happen in the buffer solution. The weak acid partially dissociated, okay, and then the salt completely dissociated. Okay, so this is the conjugate base. This is the explanation on action of acidic buffer solution to control pH. So for the first case, when small amount of strong acid is added, it will react with the conjugate base, so the ethanol ion, and then form ethanol acid, which is a weak acid. So the concentration of the buffer, so also the concentration of the H plus ion remain constant. As a result, right, only a small change in pH because the strong acid added react with the conjugate base and then produce the weak acid. So the concentration of the conjugate base decrease, the concentration of the weak acid increase. Okay, when strong base is added, so strong base will react with the ethanol acid, the weak acid, so to form the conjugate base and water. So the strong base consumed by the reaction with ethanol acid. So the concentration of the ethanol acid decrease and then the concentration of the conjugate base increase. As a result, there will be only a small change in pH. Okay, tutorial question 14. Be careful, calculate the ratio. The question asks about the ratio for ammonia to ammonium chloride, means the weak base to conjugate acid, needed to form when a buffer solution with pH of 8.3. So over here, we have to write Henderson-Hasselbalch equation. Given, okay, is pH 8.3, but this question is with ammonia weak base, so we have to calculate the pOH. So the pOH of this system is 5.7, okay, equal to pKb plus log conjugate acid over weak base. So this is the, if according to this Henderson-Hasselbalch equation, the ratio that we get is ammonium to ammonia. So the answer is 9. But now the question asks about ammonia to ammonium chloride. That's why we reverse it, become the answer 1/9. Yeah. So you must train yourself, press the calculator correctly. Yeah. So the ratio of ammonium to ammonia is 9. But the question asks about ammonia to ammonium chloride. So you just reverse. Okay, tutorial question 15, calculate pH. Okay, so this is the concentration for the weak base. So this is concentration for the conjugate acid or the salt in the buffer solution. What would the pH be after the addition of 20 ml of 0.05 molar sodium hydroxide? So this is, you need to find the pH before strong base is added and after strong base is added. So and then check what is the difference. So given the volume of the buffer solution is 80, so meaning that we need to find out the number of mole for ammonia, number of mole of ammonium chloride, and the new concentration for the solution. The final concentration of the solution 80 plus 20 is equal to 100. We also need to find out the number of mole of the sodium hydroxide and then form ice table and then check the new number of mole for ammonia, new number of mole for the conjugate acid, and then find out the pH by using Henderson-Hasselbalch equation. So let's check before. So write down the Henderson-Hasselbalch equation and then substitute the value and then we get 9.18. So this is the pH before addition of sodium hydroxide. Simple. pH after addition of sodium hydroxide. So we have to write down the equation. Ammonium will react with the strong base, so form ammonia and water. So water ignore. So this is the new number of mole, mv per thousand for ammonium. This is the new number of mole for the, no, this is a strong base is added. So this is the number of mole for the hydroxide. So this is a new number of mole for ammonia. Okay, so this is the limiting reactant. So minus 1 times 10 to the power of negative 3 mole minus, this is plus 1 times 10 to the power of negative 3 mole. So this is a new or final number of mole for the conjugate acid and weak base. So initially is 80 plus 20, so 100 ml. 100 ml must change when we want to find the concentration. Must change to liter. So this is the new concentration for ammonium. This is the new concentration for ammonia, conjugate acid. This one is weak base. So write down the formula, substitute. So pH equal to 14 minus pKb plus log. Okay, substitute the value, you get 9.21. Here. So this is the pH after the addition of sodium hydroxide. That's all for this video. Please do remember, subscribe, like, and share. If you have any question, please don't hesitate to consult with your lecturers. Stay at home, stay safe. Bye.